Right now, as you're watching this video, Neptune is screaming. Not literally, of course, but the evidence captured by the James Webb Space Telescope tells a story so violent, so unprecedented, that it's rewriting everything we thought we knew about planetary collisions in our solar system. What you're about to see isn't a computer simulation or an artist's rendering. This is real footage of the aftermath of a cosmic catastrophe that released energy equivalent to millions of nuclear bombs, and the scars are still fresh across Neptune's entire atmosphere. In the vast silence of space, Neptune has always been one of the least understood planets in our solar system. It sits so far from the Sun that even our most powerful Earth-based telescopes struggle to capture more than faint blue outlines of its storms and hazy atmosphere. For decades, Neptune was simply a distant giant, mysterious and cold, with only the occasional glimpse provided by Voyager 2 during its flyby in 1989. Since then, very little about the planet had changed in our knowledge until now, when the James Webb Space Telescope turned its gaze toward Neptune. Scientists expected to refine what we already knew: its turbulent weather patterns, methane-rich atmosphere, and faint icy rings. But instead of routine data, Webb recorded something truly shocking. Its powerful infrared eyes revealed anomalies that did not fit Neptune's usual atmospheric fingerprint. Webb detected a sudden burst of thermal radiation, unmistakable signs of heat erupting through Neptune's clouds. Alongside this, light. Variations rippled across the upper atmosphere, appearing and disappearing as though the planet itself had been struck by some invisible force. These signals were not random noise. They were consistent, powerful, and far too unusual to be dismissed. Astronomers immediately knew something extraordinary had happened. The data showed a massive energy release, one that could not be explained by normal weather activity or solar heating. Instead, the evidence pointed to a violent external cause. And as researchers compared Webb's infrared readings frame by frame, a startling conclusion began to emerge. Neptune had likely experienced a colossal collision with a gigantic object. This was no small impact, like a meteor burning through Earth's sky. The signatures suggested something much larger, a body big enough to disturb Neptune's entire atmosphere. The shockwaves Webb recorded hinted at an impact event of planet-shaping proportion, the kind of collision that could leave long-lasting scars on the gas giant. For scientists watching the data unfold in real time, it was a historic moment. Neptune, a world so distant that it takes sunlight more than 4 hours to reach it, was suddenly revealing one of the most violent events in modern planetary science. And thanks to the James Webb Space Telescope, humanity had a front-row seat to witness it. The first clue of Neptune's collision came in the form of heat, intense, unnatural heat. Normally, Neptune is one of the coldest planets in the solar system, with average temperatures plunging below -200 degrees Celsius. Its atmosphere, dominated by hydrogen, helium, and methane, traps very little warmth from the sun. But when James Webb scanned the planet, its sensors revealed something that no astronomer expected to see: a sudden and powerful surge of thermal radiation erupting from the upper layers of Neptune's clouds. This spike in energy could not be explained by the planet's normal weather cycles. Neptune's storms, while violent, are fueled by internal heat and sunlight absorbed in the atmosphere. Yet the readings from Webb showed something different: an enormous injection of energy, as if a foreign object had smashed into the atmosphere and released unimaginable amounts of heat in an instant. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. Even more astonishing was what followed. Webb's infrared detectors recorded rippling shockwaves moving outward across Neptune's gaseous layers. Imagine tossing a massive stone into a still lake. The ripples expand in every direction. Now, Replace the lake with Neptune's atmosphere and the stone with a cosmic intruder, and you begin to understand the scale of what Webb witnessed. These shockwaves did not pass unnoticed. They left behind clear distortions in the planet's structure, disrupting jet streams and shifting cloud patterns. For the first time, astronomers could see visible scars etched into Neptune's weather system. Massive bands of clouds stretched and twisted in unnatural ways, marking the path of the disturbance. It was as though Neptune itself had been bruised by the colossal force of the impact. The phenomenon was unprecedented. On Earth, shockwaves from large impacts can shatter rock, trigger tsunamis, and alter climate for years. On Neptune, a world with no solid surface, the effect was even more dramatic. The impact energy spread through the thick atmosphere, dispersing heat and turbulence across a planet 4 times the diameter of Earth. Webb's instruments recorded it all in exquisite detail, giving scientists the first-ever glimpse of how an ice giant reacts when struck by a massive intruder. What makes this discovery even more profound is the rarity of such events. Collisions of this scale are not everyday occurrences. For Webb to capture one so vividly and in real time suggests we are witnessing a cosmic event that may happen only once in many thousands, perhaps even millions, of years. It was as if Neptune, usually a distant and silent giant, suddenly shouted. Across the solar system, something extraordinary has happened here. Once the evidence of heat and shockwaves was confirmed, the question became unavoidable. What exactly hit Neptune? To release such an enormous amount of energy, the colliding body had to be far more than a simple chunk of rock or ice. It wasn't. A meteor, the kind that burns harmlessly in Earth's skies. This was something far larger, far more powerful. By carefully analyzing the thermal radiation and the spread of shockwaves, scientists began estimating the size of the object. Their conclusion was staggering. The impactor was likely tens, possibly even hundreds, of kilometers across. To put this into perspective, an object just 10 kilometers wide is believed to have wiped out the dinosaurs on Earth 66 million years ago. The body that struck Neptune could have been 10 times larger, carrying with it energy on a scale almost beyond imagination. But where could such a giant have come from? Astronomers pointed their attention to the Kuiper Belt, a vast region of icy debris and dwarf planets orbiting beyond Neptune. This is the same area where Pluto resides, along with countless frozen bodies left over from the birth of the solar system. Occasionally, gravitational nudges from Neptune itself can dislodge one of these icy wanderers, sending it spiraling inward on a deadly trajectory. Another possibility is that the intruder was a rogue comet, a body set adrift through the solar system, wandering for millions of years until it crossed Neptune's path. With Neptune's immense gravity, 17 times stronger than Earth's, it would have been almost impossible for such a traveler to escape capture once it came close. Instead, it would have been drawn inward, accelerating to incredible speeds, before slamming into the planet's thick atmosphere. Events like this are not only violent, they are also extraordinarily rare. In the modern solar system, collisions of this magnitude are thought to happen on timescales of millions of years. To actually witness one, and with such advanced instruments as the James Webb Space Telescope, is a stroke of cosmic luck of the highest order. What makes this even more remarkable is that Neptune may now serve as a natural archive of the collision. Fragments of the impactor could remain suspended in its atmosphere, detectable as strange chemical signatures. For scientists, this means Neptune is not just a planet, but a time capsule, holding within it material from the solar system's outer reaches, or perhaps even from beyond. In a single event, Webb allowed us to look back in time and glimpse the chaotic processes that once shaped every world we know. For Neptune, this collision may be one chapter in a story of repeated cosmic encounters. And for us, it is a vivid reminder that even in today's seemingly stable solar system, the echoes of creation are still being written in fire and ice. On Earth, an impact leaves behind a scar of stone and ash. On Mars, craters and dust storms testify to violent collisions from ages past. But Neptune is different, profoundly different. This distant giant has no solid crust for an object to slam into, no bedrock to capture the mark of destruction. Instead, Neptune is a world of pure atmosphere, a planet made almost entirely of swirling hydrogen, helium, and methane gases. And so, when the intruder struck, the outcome was unlike anything we have ever witnessed on another planet. The massive body did not carve a crater or scatter boulders across a barren plain. Instead, it was swallowed alive, pulled into Neptune's deep gaseous layers, where the crushing density of the atmosphere tore it apart. Piece by piece, the impactor dissolved until its tremendous energy, accumulated over billions of years of travel through space, was released in a single, devastating instant. The sheer violence of that release is difficult to comprehend. Astronomers estimate that the impact unleashed energy on a scale equivalent to millions of nuclear bombs exploding at once. Imagine the combined destructive force of all the weapons humanity has ever created, multiplied many times over, erupting in a single moment. And even then, you would only be scratching the surface of the power involved. What followed was not a single explosion, but a chain reaction reverberating throughout the entire planet. The heat pulse surged upward, igniting violent chemical reactions in Neptune's upper atmosphere. Layers of methane and hydrogen were ripped apart and recombined, forming clouds of strange new compounds, molecules that had never been seen there before. For the first time, astronomers could directly observe the chemistry of an impact on an ice giant, revealed through the James Webb Telescope's sensitive infrared eyes. Unlike a rocky world, Neptune could not preserve a permanent crater as a memory of what had happened. Instead, the evidence was etched into its weather. Webb captured the aftermath, vast atmospheric scars, swirling with turbulence, stretching thousands of kilometers across. Clouds that had been stable for years were shredded and scattered, familiar storm systems twisted out of shape, and new ones formed seemingly overnight. Astronomers even noticed shifts in Neptune's iconic dark spots, suggesting that the impact had reshaped the very circulation of the planet's winds. The scars were not only visible but lingering. Pockets of extreme heat continued to radiate from the entry point long after the object had dissolved. Massive ripples of turbulence echoed outward, disrupting jet streams that circled the planet at incredible speeds. In some regions, the haze at high altitudes darkened, creating unusual shadows and color changes that had never been recorded before. Neptune, usually serene in its cold blue hues, now appeared bruised, its atmosphere marked by the hand of violence. For scientists, this was a revelation. They had long theorized what a giant impact on a gas or ice giant might look like, but no one had ever seen it so clearly. Here was proof that Neptune could be scarred, not in stone, but in air, chemistry, and motion. The planet itself had absorbed the impact, reshaping its atmosphere in ways that may take decades or even centuries to settle. On Earth, such a collision would have ended life as we know it. On Neptune, it became something else entirely, a cosmic experiment on a planetary scale, a glimpse into how the solar system's most mysterious worlds evolve under the force of violence. And thanks to the James Webb Space Telescope, humanity now has the first clear record of such a rare and extraordinary event. In the silent darkness beyond Neptune, the James Webb Space Telescope did more than just capture a flash of heat. Its powerful infrared spectrometers allowed scientists to peer directly into the chemical chaos left behind by the collision. What they found was astonishing. Webb revealed that the impactor had not simply vanished into Neptune's vast blue atmosphere. Instead, it had seeded the skies with new molecules and elements, foreign material that had traveled across the solar system and now blended with the chemistry of the ice giant. This was the moment when Neptune, for the first time in recorded history, was marked by the fingerprints of a visitor from the Kuiper Belt. Among the most striking discoveries were unusual signatures of ammonia and carbon dioxide, compounds not normally found in significant quantities in Neptune's upper atmosphere. There were also subtle but unmistakable variations in methane, a gas that usually dominates Neptune's chemistry. These shifts hinted at violent reactions triggered by the immense heat of the collision, rearranging Neptune's atmospheric recipe in a matter of seconds. But the surprises did not end there. Webb's instruments also suggested the presence of exotic ices and hydrocarbons, the kind of fragile compounds believed to exist in the frozen depths of the Kuiper Belt. These are materials forged in the coldest regions of space, where sunlight is weak and temperatures plummet to near absolute zero. For scientists, it was like being handed a sample of the outer solar system's chemistry, delivered directly into Neptune's skies by a cosmic messenger. This discovery was more than a curiosity, it was a revelation. Each molecule detected acted like a clue to the origin of the impactor. Was it a fragment of a Kuiper Belt dwarf planet, a rogue comet on a long, wandering orbit, or perhaps even a remnant of the early solar system, a survivor from the chaotic days when the planets themselves were still forming? By analyzing the chemical fingerprints left behind, scientists could begin to reconstruct the story of where this object came from and what it was made of. The chemical chaos also told them something about Neptune itself. When the impactor dissolved into the atmosphere, it plunged deep, stirring layers of gas that rarely interact with the upper skies. In doing so, it dredged up hidden materials from Neptune's interior, compounds normally locked away beneath crushing pressure. Webb detected hints of these as well, suggesting that the impact had temporarily opened a window into the secret chemistry of Neptune's deeper layers. For planetary scientists, this was extraordinary. They were not just studying a collision, they were, in effect, running a cosmic laboratory experiment, one that would be impossible to reproduce on Earth. A Kuiper Belt body, untouched for billions of years, had been smashed open. Its chemistry spilled across Neptune's clouds, then analyzed by Webb from 1,000,000 miles away. These fingerprints may fade over time, dispersed by Neptune's violent winds, but for now, they remain a record of both the impactor's identity and Neptune's hidden depths. Every molecule tells a story of icy origins, of violent transformation, and of a planet still being shaped by the forces of the solar system. And in that sense, Neptune's skies have become something more than just clouds of gas. They are a canvas of chemistry, painted by the hand of a collision that traveled millions of miles, only to end in a firestorm that Webb captured in exquisite detail. Neptune is already a world defined by extremes. Even before the collision, it was known for its fastest winds in the solar system, howling at speeds over 1,500 miles per hour. Storms larger than Earth itself swirl across its cobalt-blue atmosphere, and the planet's dynamic cloud systems constantly shift, forming dark spots and bright bands that appear and vanish over months. It is a planet in constant motion, a living laboratory of turbulence. But when the massive impactor struck, it fundamentally altered the balance of Neptune's already violent atmosphere. The energy released by the collision was not confined to a single location. It spread across the planet, injecting heat and momentum into the wind systems like an invisible hand accelerating the storm. Suddenly, the familiar patterns of Neptune's weather were disrupted, giving birth to new storms far stronger than anything observed before. Webb's infrared and visible light instruments revealed the aftermath in stunning detail. Bright new spots appeared across the planet, areas of intense heat and activity that were previously absent. Long, elongated clouds stretched across thousands of kilometers, shaped by winds that had been supercharged by the impact. Even Neptune's iconic dark spots seemed to shift in response, as if the planet itself was adjusting to the energy that had been unleashed. The collision also created massive vortices, spinning storms of a size and intensity unprecedented on Neptune. Some of these storms rotated so rapidly that they could generate wind speeds rivaling or even surpassing the planet's normal maximums. Webb detected swirling turbulence, chaotic cloud patterns that suggested the atmosphere was still, trying to stabilize months after the impact. Scientists speculate that these storms may persist for years, gradually dispersing the energy from the collision while leaving a permanent mark on the planet's weather system. The implications are profound. Neptune is a planet whose behavior is largely hidden from Earthbound observation, and yet this single impact gave astronomers a rare opportunity to watch how an ice giant responds to a sudden influx of energy. By studying these supercharged storms, researchers can learn not only about Neptune itself, but also about the physics governing gas and ice giants across the galaxy. In effect, the impact turned Neptune into a planetary-scale experiment in extreme meteorology. The energy, momentum, and chemical fallout all combined to create a dynamic system unlike anything seen before. Webb's instruments captured it all: the bright spots marking bursts of heat, the elongated clouds stretched by furious winds, and the swirling turbulence hinting at storms far larger than anything previously catalogued. For scientists and the rest of us watching from millions of miles away, the lesson is clear. Neptune is not just a distant, cold giant. It is a living, breathing world, capable of dramatic change, whose extreme weather can be supercharged by events that ripple through the outer solar system. And thanks to the James Webb Space Telescope, humanity now has the first-ever front-row seat to witness this cosmic drama unfold. The collision on Neptune was not an isolated event. While the planet itself absorbed the bulk of the impact, the surrounding system, its 14 moons and delicate ring network, could not remain untouched. These moons, ranging from tiny, irregularly shaped rocks to the massive and mysterious Triton, are bound by Neptune's gravity in a delicate celestial dance. The impact unleashed a torrent of energy and debris, a violent disturbance that may have resonated throughout the system. Webb's sensitive instruments suggest that dust, ice particles, and fragments from the impactor may have been ejected far beyond the upper atmosphere, drifting outward into the ring plane. Neptune's rings are faint and wispy compared to Saturn's, but even subtle changes can be detected. Scientists theorize that this influx of material could have temporarily thickened certain sections, brightened faint arcs, or created transient streaks visible in the infrared spectrum. Each fragment of debris acts as a cosmic fingerprint, a IDE, direct record of the colossal impact and the chaotic forces it unleashed. Meanwhile, the moons themselves may have experienced both physical and chemical changes. Smaller moons, constantly bombarded by micrometeorites, may have received a fresh coating of material from the collision, slightly altering their surfaces. Triton, Neptune's largest and most enigmatic moon, could have been particularly affected. Its icy surface and tenuous atmosphere might have interacted with fallout from the impact, sparking chemical reactions in the ice, and perhaps even temporarily altering its thin nitrogen atmosphere. The collision's energy may have also introduced minor gravitational perturbations, subtly nudging the orbits of moons and sending ripples through the system. The interconnectedness of Neptune and its satellites underscores a remarkable truth. In a planetary system, nothing exists in isolation. A single extraordinary event on the planet can cascade outward, affecting rings, moons, and even the dynamics of the surrounding space environment. By observing these changes, astronomers gain a rare opportunity to study planetary system evolution. In real time, an invaluable look at how energy propagates through a complex, interrelated system of gas, ice, and rock. Moreover, the potential long-term consequences are profound. Rings that are temporarily brightened or thickened may gradually settle back into their original configuration, but subtle changes in moon surfaces or orbits could persist for decades or even centuries. Over time, the system may appear subtly, different to future observers, a permanent record of a single violent encounter that occurred millions of miles away from Earth. This impact reminds us that Neptune is far more than a distant, cold blue world. It is alive with motion, chemistry, and gravitational complexity, a giant that responds dynamically to external forces. Every moon, every icy ringlet, every cloud in its atmosphere reacts to the energy unleashed. Webb has provided humanity with a front-row seat to witness this cosmic interplay, capturing a rare moment when a distant ice giant, its moons, and its rings were collectively reshaped by a single cataclysmic event. In essence, the collision serves as a vivid reminder that the wheezy solar system is a living, dynamic environment where even worlds at the very edge are constantly evolving, reacting, and transforming. Neptune, once considered a quiet sentinel in the outer reaches of our solar system, has shown itself to be a planet of dramatic consequences, a system where every impact, no matter how distant, leaves a lasting impression on the entire celestial neighborhood. Collisions are not just random accidents in the cosmos. They are one of the most fundamental forces that shape the evolution of planets. From the early chaotic days of the solar system to the present, impacts have played a key role in determining planetary atmospheres, surface chemistry, rotation, and even the development of moons. Each collision carries energy, material, and sometimes life-altering ingredients across the vastness of space. Neptune, with its thick gaseous layers and extreme environment, is no exception. While it may seem distant and cold, it is an active world constantly reshaped by external forces. A single massive impact, like the one captured by Webb, has multiple profound effects. First, such collisions can deliver essential volatiles, including water, ammonia, methane, and organic molecules carried from distant regions like the Kuiper Belt. These ingredients may seem minor, but over time, they contribute to the chemical complexity of the planet's atmosphere. The impact also alters magnetic fields and rotation dynamics. As energy is transferred through Neptune's interior, subtle changes in rotation or shifts in the planet's magnetosphere can occur, influencing how charged particles move through its upper atmosphere and affecting long-term climate and storm patterns. Even the planet's atmospheric circulation, from winds to storm intensity, is reshaped, leaving long-lasting signatures of energy and turbulence. Beyond Neptune itself, this event provides a living example of how planets continue to evolve long after their initial formation. Unlike the early solar system, when collisions were frequent and catastrophic, today's impacts are rare. But when they do occur, their effects ripple across planetary atmospheres, moons, and rings, reminding us that no planet is static. Each collision is a cosmic experiment, showing scientists how energy, momentum, and material are redistributed throughout a planetary system. Studying such impacts allows astronomers to draw parallels with exoplanets far beyond our solar system. Understanding how Neptune responds to a single collision helps us predict how similar ice giants, common throughout the galaxy, might behave under extreme conditions. Webb's observations are not just about one moment in time, they are a window into the life cycles of planets, illustrating that even giants at the edges of their systems remain active, dynamic, and constantly evolving. In essence, this collision is a reminder that planetary evolution is ongoing. Planets are not frozen relics of the past. They are living, breathing systems, shaped by interactions both violent and subtle. Each impact, whether massive or minor, leaves a trace, gradually, sculpting worlds and ensuring that the cosmos remains a theater of constant change. The collision on Neptune offers more than just insight into our own solar system. It provides a unique window into the lives of distant worlds. Over the past 2 decades, astronomers have discovered thousands of exoplanets orbiting other stars, many of which are classified as hot Neptunes or mini-Neptunes. These planets, often similar in size and composition to Neptune, but much closer to their stars, display atmospheres and chemical signatures that are sometimes puzzling. By observing a real-time impact in Neptune's atmosphere, Scientists now have a baseline for interpreting sudden anomalies on distant exoplanets. For example, if an exoplanet's atmosphere unexpectedly brightens or shows new chemical compounds, astronomers can compare these signatures with Webb's observations of Neptune to determine if a recent collision might be responsible. This is revolutionary because it transforms speculative theories about exoplanetary impacts into data-driven science. The specific molecules Webb detected on Neptune, ammonia, methane variations, exotic ices, and other volatiles, serve as reference points for interpreting exoplanet spectra. Previously, unusual chemical readings could be misattributed to exotic atmospheric processes, but now scientists can identify whether these anomalies are the fingerprints of collisions with large bodies, like Kuiper Belt objects or rogue comets. Moreover, the Neptune impact provides clues about planetary system evolution beyond our solar system. In tightly packed exoplanet systems, where gravitational interactions are more intense, collisions may be more frequent. Understanding how Neptune responds to a massive impact, how its atmosphere absorbs energy, how rings and moons are disturbed, and how chemical fingerprints are distributed, allows astronomers to predict the consequences of similar events on exoplanets, even when those worlds are hundreds of light-years away. This event also underscores the importance of long-term monitoring of exoplanet atmospheres. Just as Webb caught a rare moment on Neptune, future telescopes can detect transient events on distant planets. By building a catalog of collisional signatures, scientists can reconstruct the history of planetary bombardment in other systems, offering insights into how planets gain or lose atmosphere, how moons form or are altered, and how planetary climates evolve under extreme conditions. Ultimately, Neptune's collision is a reminder that planetary evolution is universal. What we witness in our own solar system provides a laboratory for understanding worlds far beyond it. Each giant impact teaches us about the dynamic nature of planets, the role of rare but transformative events, and the intricate interplay of chemistry, physics, and gravity that shapes every celestial body. Webb has given humanity a front-row seat, not only to Neptune's drama, but also to the cosmic processes that likely unfold across billions of other planetary systems. By studying this single event, scientists can now connect the dots between local observations and distant exoplanet mysteries, turning what was once theoretical into concrete, observable science. It's a vivid reminder that in a universe filled with planets, moons, and wandering icy bodies, chaos and collision are essential to the story of planetary life, whether near or light-years away. The Neptune impact has revealed a side of the James Webb Space Telescope that few had fully appreciated. While it was designed to peer into the furthest reaches of the universe, capturing light from the earliest galaxies and unraveling the story of cosmic evolution, Webb has also proven to be a remarkably capable sentinel within our own solar system. This discovery showcases the telescope's ability to operate not just as a window to the past, but as a real-time observer of dynamic, high-energy events happening right in our cosmic backyard. By detecting the thermal bursts, atmospheric disturbances, and chemical fingerprints of a massive impact on Neptune, Webb demonstrated an unprecedented level of precision and sensitivity. It could detect subtle changes in light and heat, track the spread of shockwaves across an entire planet, and measure the introduction of exotic molecules into the atmosphere. This is a capability that was once thought impossible for a telescope. Primarily designed for distant galaxies, showing that Webb can operate simultaneously as both deep space explorer and planetary monitor. The implications for science are enormous. Humanity now has a tool capable of observing rare, transformative events in the solar system, events that may occur only once in decades or centuries. Collisions like the one on Neptune, comet flybys, or even sudden storms on gas giants can be monitored with precision, giving scientists the chance to study planetary evolution as it happens, rather than reconstruct it from historical data or models. Webb's ability to detect these occurrences opens a new chapter in solar system science, bridging the gap between planetary astronomy and cosmology. Beyond our solar system, this capability has ripple effects for exoplanet research. Webb's sensitivity to atmospheric changes and chemical signatures allows scientists to draw parallels between local events and distant planets, helping them identify potential collisions or sudden atmospheric phenomena on worlds orbiting other stars. In essence, the telescope can act as a cosmic detective, piecing together the lives of planets both near and far by observing the subtle fingerprints of high-energy interactions. Perhaps most importantly, Webb's observations highlight a profound shift in how we understand humanity's place in the universe. For the first time, we can witness the dynamism of planets in real time, experiencing cosmic events as they unfold millions of miles away. We are no longer limited to static snapshots of distant worlds. Instead, we can monitor their ongoing evolution, chemical transformations, and the dramatic consequences of rare events that shape planetary systems. This dual role, as a window to the early universe and as a guardian of our solar system, cements the James Webb Space Telescope's legacy as one of the most versatile and groundbreaking instruments in human history. Its discoveries remind us that space is not static. Whether it's a galaxy forming billions of years ago or an ice giant like Neptune being reshaped by a massive impact today, the universe is alive with motion, energy, and change. In the end, Webb has not only expanded our knowledge of distant galaxies, stars, and exoplanets, it has also expanded our awareness of the immediate, dynamic cosmos around us. From the violent collision on Neptune to the storms that rage on distant worlds, Webb stands ready to capture the universe's most dramatic moments, proving that the cosmos is far more active, connected, and fascinating than we ever imagined. Humanity now has a telescope capable of tracking the universe's most extraordinary events, turning science fiction into science fact, and giving us a front-row seat to the ongoing drama of our solar system and beyond. With Webb watching, we are not just observers of history. We are witnesses to the universe's living, evolving story. From Neptune's sudden, violent collision to the lessons it teaches us about distant exoplanets, this discovery reminds us that the universe is alive, dynamic, and full of surprises. The James Webb Space Telescope has shown us that we no longer need to rely solely on theories or static images. We can watch cosmic events unfold in real time, capturing moments that were once beyond human reach. Every impact, every storm, and every chemical fingerprint is a story waiting to be told. And Webb gives humanity the ability to read it. We are witnessing not just the evolution of a planet, but a broader narrative about how planets, moons, and entire systems continue to change, even billions of years after their formation. As we look to the skies, we realize that the cosmos is not a distant, unchanging stage. It is a living theater where collisions, storms, and explosions continually shape world. And now, with Webb as our eye in the sky, humanity has a front-row seat to the greatest show in existence. So, as we marvel at Neptune, remember, the universe is full of wonders still waiting to be discovered, and every new observation brings us closer to understanding our place among the stars. If this journey through Neptune and beyond fascinated you, subscribe to our channel to witness more cosmic mysteries, and leave a comment sharing which planetary discovery excites you the most. The universe is unfolding, and we're here to explore it together.